Okay, welcome all to the next edition of Code Seminar. Today we have Petr Šťastný, who will talk about symbolic execution of interpreted languages. Thank you.
So, good afternoon, and let's start. Symbolic execution is a program testing technique that enables one to effectively test programs and infer their behavior very maybe complex or way too big to test and find each case using more traditional techniques. How it works is when we have a program and we execute it in a classic way, we feed some concrete, specific values to it as an input. For example, we have a function that takes a single integer, and if the integer is equal to some magical number, the function would throw an error. We are very unlikely to find this specific case via traditional fuzzing or similar methods, because it's just unlikely that we will have this specific number. So symbolic execution is an answer to this kind of problem. During the traditional execution, we would feed a specific value to the variable I and run the function, while in symbolic execution, we do not feed a specific value to I, we feed there some generic symbol. So let's, for example, say that the input of the function is some symbol alpha. And whenever we do any operation on the variable, we update the symbol accordingly. So for example, if in here we were multiplying the number by 2, we would progress in the symbolic execution of the function by assigning a double the initial assignment to the variable. So this way we can model modifications of the values as we progress through the program. What do we do when we encounter a branch? In normal generic execution, we would just evaluate the value and decide whether the condition holds or not, and potentially skip this part. In symbolic execution, however, we may or may not hit the branch based on the value of alpha, which is variable. So in this case, we actually split into 2 separate states. Into one state when we set alpha to such a value that we hit the condition, and the second state where we do not. So in both states, we still have the same assignment, but in this one, where we hit the branch, we will add the path condition that tells us that 2 times alpha must be equal to 42. When we encounter such a branch, we will have a set of these conditions that essentially represent how we traverse through the program and all the branches that we hit and all the paths we took. So when we encounter such a condition, we can try to solve this set of conditions to essentially know whether the path, even if the branch even can be taken on. So for example, if there was an assertion or something like that, we could just solve these equations to know whether the assert can fail under some inputs, given the path that we took. So that's the basic symbolic execution, and there are several problems with it, most of them performance-wise. This technique is quite heavy on computational resources because it invokes the SMT solver quite often, which is a slow operation, particularly if we were to have some non-linear stuff in there. So if we want to execute even large programs, we have to apply some non-trivial optimizations. I will talk about them later, but there are plenty of them and they are quite hard to implement. However, it is possible. For example, I believe that Microsoft has been using this technique since like 2008, and it's running basically non-stop since then, and this technique alone has found about 30% of all bugs that Microsoft found by some kind of automated testing. So it's quite powerful, but it requires heavy investment in the building of the symbolic execution engine that would run fast enough. So there are several symbolic execution engines. For example, S2E, which I used in my thesis, works on the compiled program representation. So it can execute not only like C or some other specific language, but basically anything that can be compiled via LLVM to something, which is quite cool. But that only works for some compiled languages. It doesn't work for interpreted ones. And that's the aim of this talk. I will tell you how to adapt existing symbolic execution engines so they can handle interpreted languages. The key idea is that if we were to build an engine, symbolic execution engine for interpreted language, it would be quite hard, it would take a long time, and we would want to build an engine that essentially simulates the interpreter because we want back-for-back compatibility with the original interpreter. So that's hard, and the solution to that is to not execute the program itself, but to execute the interpreter of the interpreted language. We can symbolically execute the interpreter of, say, R, and then feed the R script that we actually aim to test as an input. So how it looks is that we have some high-level and low-level statements in the program. In high-level R, we have, for example, let's say, okay, this is R, but let's say we can have some high-level statement like this in our interpreted language, and this will map the huge number of low-level statements in the interpreter. So if we put an array, if you put some symbolic variables in there, we would be able to use symbolic execution engine to execute it, and that's it, problem solved. The issue is, of course, the performance. The interpreter is really, really large. There is lots of stuff before and after it, and the statement itself will map to a huge number of low-level instructions. So how to solve that? If we just ran symbolic execution on the interpreter, we would probably hit a case where it would get stuck somewhere here in the parsing stage, which actually happened to me, or something similar, and we would never actually get to the actual code that is interesting to us, or we would execute it really, really slowly, which is not desirable. So what we can do is we can add some heuristics that will choose the correct state to go from. When we execute something symbolically, we'll generate a huge amount of states, and we want to select the interesting ones that we want to continue from in order to explore the program quickly. There are a number of heuristics. The one that is used in Chef, which is the tool that does this stuff with the interpreted languages, is Cuba, classic from path analysis, and it works like that. Essentially, we have some huge number of states in some sort of tree, and we divide those states into separate classes. Those classes may have different sizes, and we choose one class uniformly at random, and then choose some state from the class to execute. What this does is we can, for example, group low-level statements by the high-level statement they correspond to. So if we had 10 high-level statements here, we could group those low-level statements that the symbolic execution engine sees into groups based on the high-level statement, and execute them using this strategy, which ensures that we do not spend over a long amount of time executing just one single high-level statement that may be like computationally expensive in terms of like number of low-level instructions because of the implementation, but we will cover all of them more or less the same amount of time, which is much better. We can even employ this strategy multiple times to, for example, primarily base those classes on the high-level instruction and secondarily on the low-level instruction. So, for example, if there is a loop, we do not want to get stuck in it, or if there is, for example, some call to a non-native function, we don't want to get stuck in it. So we want to prioritize other instruction if it spawns too many of them. So this is one issue solved, but there are multiple other ones. One of them is, for example, hashing. In quite a number of interpreted languages, there is some use of hash-based data structures in the interpreter. And this is not very good for SMT solvers because it's nonlinearity that will take them a very long amount of time to solve. So we need to solve that. When I implemented this thing for R, I had a problem when during executing the first high-level instruction, it got stuck essentially forever and would never do anything else. And the issue was hashing because it was doing some variable lookup, and that triggered lookup of the hash data structure, which is bad. So what one can do is find all all hashing functions in the interpreter and simply replace them to return 0 or something like that, which will essentially degrade all data structures to linked list or something similar, which may be slow to execute under normal circumstances, but symbolic execution will handle it much better. And those two changes were enough to actually execute small to medium sized R programs. So this is a key component and it cannot be left out based on my own experience, which is, yeah, quite interesting. Another thing that we have to consider is some sort of handling the environment. After all, we are not dealing with some idealized functional code, we are dealing with real-world programs. Microsoft has managed to fast Microsoft Office with it, so it needs to communicate with the environment. So how do we do that? There are several approaches to it. Some symbolic execution engines, for example, Dart, simply concretized all calls to foreign functions. So, for example, if it's called malloc or something it didn't have implementation for, it would concretize the symbolic variables that went into it, which is not quite effective, not what we want while it is fast. It tends to miss a lot of paths afterwards because we only get a concrete value out of it and not symbolic one. So this defeats the purpose of symbolic execution. Then we can have we can simply implement these functions ourselves. How many syscalls are there to implement? Like 150 or so, which is certainly within the realm of possibility to do by hand. And that's what CLI authors did. They managed to implement a large part of this interface symbolically. So, for example, they wrote their own symbolic file system, where if you use read or write of some file with a known name, it would do the usual stuff. But if you did it with a symbolic string, what CLI would do is it would have during the whole execution, it would have and separate symbolic files. And if you access a symbolic file, it would spawn n states. Each of them would access one of the n symbolic files, and then n plus first state if it's returned an error. But CLI authors managed to implement essentially the whole interface like this and managed to fast, for example, do Linux core utils using that, which is remarkable. And it actually worked really, really well. But it's a lot of manual work and we do not want to do this. So what do? We use the brute force approach that S2 used and we just virtualize everything. S2 works by running this analysis inside QEMU. And whenever, for example, we fork because we create a new state, it will fork the whole QEMU with the whole system inside it. So we do not have to do any additional work. We don't have to like model the system. We do not have to worry that we will make some errors or we will create some inconsistencies because, well, everything is modeled by QEMU completely correctly. So it's perfect, and the only issue is that it's extremely slow. S2E again solves this in a very elegant manner, and that is concolic execution. This basically works by mixing together symbolic and concrete execution in a clever way so that we do not have to do so much work. S2E uses what's known as selective symbolic execution, and it works like that. We have a huge system with a great number of various modules and libraries and system components, and we only care about a small thing in the middle, for example, the interpreter. And we do not care about anything else. We do not want nor need to symbolically execute it because it would just take up time and we would never do anything. So what S2E does is that it can switch between symbolic and concrete execution and can, for example, execute some part of the code symbolically, then jump to some other component, execute concretely, which is extremely fast, and then return back and continue with the symbolic execution that is slow but precise. So how do we do that? There are essentially two cases. First case is that we are in some concrete module A, and we are calling to a symbolic module B. So how do we do that? Well, we can just execute the symbolic component concretely and return the value. We do not essentially have to do everything. This is a trivial case. If you want to, we can still execute the symbolic component completely symbolically, but we will return the concrete value. So there's not much to be done here. The more interesting case is when we are like here, when we are in a symbolic module and we are calling a concrete one. So how do we do it without losing precision? We could just, for example, take the values of variables we have. We could take the path conditions and concretize inputs for the module. That would produce some concrete value that satisfies the conditions. We could run the module and then return the result. It's fine, it would work. However, it would impact correctness. First, we may enter some extra branches afterwards that we are not supposed to enter. From the concrete module, we return some value, and we might have not taken into account some path conditions that would affect the input variables. So, because we concretize it, so we need to record what's going on in there. And second, it's more interesting, we may leave out some branches that may still be reachable because we just got back some concrete value from the concrete subsystem. So it may happen that there might be a branch that would rely on some specific value being returned, but we didn't return something a bit else, so we do not enter it, which is not what we want. So how does S2E handle it? Whenever we have some concrete values, conditions that arise from the concrete module, we mark them as soft conditions. And whenever we would not enter a specific branch because of a soft condition, we know that it might be a false negative, and we can simply return back and execute the module again with different inputs and possibly find out that we actually can enter the branch and we just didn't know it. So that's the way S2E models it, and actually works really well. S2E was a system that was used to, for example, symbolically execute Microsoft Office, so it worked really, really well. So that's one way of symbolic execution. There is another one that is used by other symbolic execution engines, and that is dynamic symbolic execution. It essentially works by using concrete execution to guide the symbolic execution search process. So for example, if we had some program, what we could do is to run it with some concrete input. So it would take some paths and something, and during this we would record the symbolic, what happened, and we would record the path conditions that we had to. We don't have to run the symbolic, the SMT solver at this stage because we are just executing concretely, but we are remembering what happened. And afterwards, when we run it, we can somehow, using some heuristic, pick some branching point and use SMT solver and the path conditions that we know about to find out which input do we need to put into the component to take a different branch. And then we can run it again and explore a different branch. So this way we can easily explore the component without using the SMT solver so much. So that's it. And yeah, there are some other issues that we need to handle. For example, symbolic pointers. We need to model memories somehow, and symbolic pointers make it really hard to do anything because they could record almost anywhere. So what S2E does is they evade the having to handle symbolic pointers by replacing malloc. Because symbolic pointers, where do they usually come from? They usually come from the allocation function that got some the amount of data was symbolic, so it returns symbolic pointer because, well, depending on how much data was requested, it could return different pointers. So it returned a symbolic pointer. So S2E does this clever thing where they replace malloc with their own implementation that, in case it received a symbolic value, it will either concretize it and just return a concrete pointer for a concrete size, or to avoid concretizing it, it can use SMT solver to find like the upper bound of the value and return a specific pointer that's large enough to hold everything. But the original size variable is still symbolic and it's not concretized, so we win either way. So that's one optimization. Another one is, for example, that Steve authors found that by reordering the clauses that we send into the SMT solver can significantly impact the performance. And if we just reorder the clauses from the least complex to most complex one, we can reduce runtime of SMT solvers by like 40% or something like it, which is. And yeah, I believe that's it. Thank you for your attention. And if you have any questions regarding this, I'll be glad to answer them.
Let's thank the speaker. Any questions?
I have a question about the performance of symbolic execution.
Yeah.
So if I understand it, so every condition or maybe other operations basically make a branching node.
Mm-hmm.
So if I have just a for loop and in it it's a if condition, so something like 20 iterations will completely kill the time, or it will take this loop.
Yes, exactly.
Yeah.
That's why you have to do proper heuristic to like choose the state carefully.
But you are still able to merge somehow the branching nodes, or?
In some cases, yes. For example, if we had if condition, we did something and then we return back, then we can merge the state that didn't branch with the one that did branch. It works by utilizing if then else conditions, which is a feature that some SMT solvers support. So, For example, if we had an if a is bigger than 5, then b is 4, else b is 3. Then we could merge those two states together to something that will assign to be something like if a is bigger than 5, assign it 4, else assign it 3. So something like that. So using some capabilities of SMT solver, we can do this kind of reasoning. We can actually merge states into something similar.
Yeah. If I may, it's like just dealing the problem because the SMT solvers are very inefficient to solve this kind of merge. So if you want to merge states, you need to choose your state carefully because otherwise it's just going to deal from the SMT solver. So it will take more time.
More questions?
Yeah, I was wondering, very nice work. I'm also completely obsessed with symbolic execution, but coming from a completely different angle. So I'm symbolically executing machine code, so really different angle. What I'm wondering here is, like when you look at symbolic execution versus testing, okay, then I see, at least on a principled level, there's two differences, right? The first difference is that you can always do symbolic execution by testing by simply enumerating all possible inputs. Yeah, and you just increase the size. And of course, there's too many. Okay, but what's interesting is that symbolic execution tries to do that and tries to be more efficient by essentially running the program. In certain cases, it can run the program on a whole very large set of inputs essentially once, right? By keeping the state information properly. Yeah. So I would be interested in if you can somehow describe, how your approach does that compare to testing, right? In relation to testing. And the second is, what's also extremely important of symbolic execution as a feature is that it's sometimes able to show the absence, right, of critical input, right, that leads to something. And now you're doing a lot of heuristics here and so on, so you might actually lose some of those opportunities, right? You will, in some cases, not be able to say, well, there is no input such that something happens. But maybe in some cases, you can actually still establish that. And I would be interested to hear about that as well. And let me add just one more thing. I'm really obsessed with this. I would also be interested in what kind of theory you actually require from SMT. Arrays of big vectors, floating point, anything else, quantifiers. That's would also, a person like me working in something like this would also give a better intuition on what you're actually doing. By just describing what is the theory that you need the SMT solver to work in, and also which part of these theories perform good and others which perform bad. That's interesting to hear.
Yeah. So to start from the last thing, I believe that CLI, which is used by S2E, which is used by me, actually requires bit vectors from the SMT solver to handle the memory. But I believe that they do not model floating points symbolically and do not require that. And I'm unsure about the rest
There
of
is
it.
a series of arrays, I think.
Yeah.
They use a series of arrays to model the memory.
So does that mean you cannot actually symbolically execute programs that feature floating?
I'm not sure how implementation of that,
So, yeah,
but I believe they do not require it. Yeah.
That's a critical issue, right? So what I'm doing, for example, I completely ignore floating points. Of course. Yeah. But you use arrays of bit vectors, for example.
I believe they do to model memory. Yeah.
Registers.
Yeah.
Okay.
So like each individual like object is one bit vector. Yeah.
Yeah. That's where you also lose performance.
Mm-hmm.
And then the testing, like how can you compare this to like when can you be more efficient than just running, fuzzing the thing?
For example, I use it to like infer types for some functions in the I library by enumerating all the inputs that didn't crash a function, and then looking at the classes of inputs to see what type did the function expect. So if one enumerated all these inputs, one could, for example, reasonably say that this function does that.
No, but I mean the opposite, right? I mean the opposite. Like when does your method that you implement here, when does it actually substantially improve over just testing, over fuzzing the whole thing, over all inputs? That's a critical question, right? For justifying symbolic execution, because you can always do it trivially, right? By just running the thing on all inputs. And if you have trivial program or trivial programs, it's faster. You just run it. Even if it's a million inputs, you run it a million times, done.
Well, I mean, I believe it's quite similar to like standard symbolic execution. If given enough time, it might enumerate everything more efficiently. And
that's why it's interesting, right? To see where in principle, right, you have, how you compact the state representation in your symbolic execution engine, right? Yeah, and the other question was about, if you can, can you give us a feel of cases where you can actually show the absence of a bug? Like there's no input such that something happens. That's a key feature of symbolic execution as well, right? Over testing.
I believe yes, it could theoretically do that if given enough time.
No, I don't believe that.
Okay, so if I may suggest, let's let the speaker not take the rest of the discussion offline.
Sorry.
No, I mean, sure, let's be fine. So let's end the speaker again. No, please continue with the discussion.